Okay, so our next speaker is Elian. Yeah, hopefully. Yeah. Yeah, he will talk about distributional robust regret optimal control. Yeah. Thank you.
Thank you. Is the mic good? Yeah? Okay. So, we're all here to celebrate Stephen's 60th birthday. And one of the most amazing things is that although his chronological age may be 60, right? If we look at how Stephen has evolved over the years, right, he's aged slightly, right, since the mid-90s, but he seems to be kind of converging to a biological age of 40. So, Stephen, may you remain forever young. But in all seriousness, I'm very grateful for the mentorship that I received from Stephen. That continues even to this day. He's had a very big impact on my life, even though he may not, recognize it. So thank you, and I look forward to the next reunion 20 years from now. Today I'll discuss some work that was actually inspired by research done here at Caltech. This is joint work with my PhD student, Feras, and former postdoc, Shu Hao. So this is their work. I'm just kind of conveying it to you. It has to do with stochastic control. So you have a physical system, a controller, and a disturbance acting on that system. Typically, and here we're going to assume the disturbance is a stochastic process. So that's a baseline assumption. In the classical paradigm, you typically assume knowledge of the underlying distribution governing this process, okay? And maybe some additional structural assumptions, like it's Markovian or independent or whatever's needed in order to kind of prove nice results, like in the LQG setting. But in practice, right, there may be ambiguity, right? If you have a random sample from which you construct an empirical estimate, that estimate is invariably going to have error, okay, especially if the sample size is small. There may also be distribution shift, right? The underlying environment might be time varying, so the data generating distribution at the time of training your controller may be different from the distribution you encounter at deployment time. Okay, so the question then is, how do you design controllers that are guaranteed to perform well, right, over a class of distributions when the underlying distribution is unknown? So that's the kind of question that we want to address. And this is not a new question. We'll propose a particular approach. So I'll start with a toy problem. Okay, so this is good for developing intuition. And then I'll present the general framework. And then if there's time, I'll show how to use this technique for data-driven control. So in the toy problem, it's very simple. It's a one-stage stochastic control problem. Okay, so it's all the variables here are scalars. So x1 is equal to your initial state x0 plus your input u0 plus your disturbance w0. And we're interested in finding a causal policy, which is a function of your state at time 0, to determine an input to minimize the expectation of this quadratic cost. Okay, so it's penalizing the state, the quadratic of the state x1 plus some measure of control effort. Right? So we're assuming that the initial state and disturbance are standard normal random variables, 0 mean unit variance. We're going to allow them to be correlated. Okay? And so we'll denote their correlation by rho, and then this fully specifies the joint distribution, right, between those random variables. So we want, again, to minimize this expected cost. So if you know the distribution, in this case the correlation coefficient, this reduces to solving a very simple problem. Okay? A little bit of calculus will give you the optimal controller, which is linear in this case because of the Gaussian assumption. But it's helpful for us instead of working out the formulae, I'll just give you some intuition. Right? So the correlation coefficient plays a very important role. Right? As the initial condition and disturbance become more positively correlated, right, the amount of control effort that's needed to minimize, right, this cost increases, right, because they're kind of adding, as opposed to negative correlation where there would be some negation between the two. Okay? So if you plot the expected cost under the optimal controller as a function of the correlation coefficient, right, you see that it increases, right, which is what we would expect intuitively. Right? So what's interesting is that when they're perfectly negatively correlated, the cost is 0. Right? Why? Well, because they perfectly negate and there's no need for an input, right? So that's kind of the most favorable kind of distribution among this class. So what do you do if the correlation coefficient is unknown, right? So one natural thing to do is to take what's known as the distributionally robust approach, which involves solving this minimax problem right? Minimize over your policy, maximize over the class of distributions, which in this case is just the correlation coefficient, expected cost, right? So the optimal controller here is kind of optimizing against the worst case distribution, which you would expect to be, right, rho equal to 1. So if you plot the expected cost of this minimax controller, you see that it's optimal in the worst case, but is actually quite conservative for other distributions, right? And so the question then is it so this makes sense if you have reason to believe that nature is in fact adversarial, right? But what if it's not? What if nature is more benign? And what if you encounter a distribution that's, somewhere else? So what do? So one natural thing is to try to minimize the excess cost, right, incurred relative to this causal controller, which has knowledge of the underlying distribution, which would result in a more balanced performance. So you can do that. We're going to do something slightly different, right? So instead of minimizing the excess cost or the difference between these two curves, we're going to suggest a slightly stronger baseline, okay? So an oracle that more strongly knows the entire disturbance, right, at the outset, knows W0 in this case, right? And so here, so this is the cost incurred by the causal controller, and this is the cost incurred by a clairvoyant or non-causal controller, which knows W0 at time 0, okay? So this is the best you can do. So if you work out the solution for that, you end up with a lower bound, right, on the green curve. And this difference you can think of as the price of causality, right, or the benefit of clairvoyance, the value of clairvoyance. So this is the gap that will minimize, right, or the expected gap, maximizing over rho, minimizing over policies, right? If you do that, you end up with a controller that has a much more balanced performance across the ambiguity set, okay? In fact, it actually corresponds to the optimal causal controller for zero correlation, right, because it coincides with the green curve right at that point. So that's the basic premise for this talk. And we're going to now generalize this to linear time varying, or time invariant systems in this case. Here, xt is our state, ut is the input, and wt is the disturbance. Again, we'll treat it as being stochastic. We're going to consider a class of controllers that are strictly causal linear disturbance feedback controllers. As we all know, these are equivalent to the class of causal linear state feedback controllers. And there's a bijection between these two, which resembles the Euler or Q parameterization. Okay? Now, but the benefit, right, of using this parameterization is the cost will end up being convex in the control gate matrices, where here you would end up with polynomial expressions and a non-convex cost. Okay. We're going to work with an input-output representation. So this is finite. This problem's finite horizon. So we'll let x, u, and w represent the finite horizon trajectories of our state, input, and disturbance process. And you can express the relationship between the disturbance trajectory and input and state using this causal linear map. Okay, so f, g, and k here are just block lower triangular matrices. Okay, in other words, causal matrices. And here, script k will let denote the space of all strictly causal controllers. Okay, this space here is the space of all non-causal controllers. The cost is quadratic, so in our trajectory, so Q and R are positive. Q is positive semi-definite, we'll assume, and R is positive definite. And again, the regret will be defined similarly as, so the regret incurred by a causal controller K, or really any controller, right, in response to a disturbance W, is just that cost minus the cost of a clairvoyant, right? So here we're optimizing over the space of all non-causal, right, or clairvoyant policies which have full knowledge of the disturbance at the outset. Okay. So the way to think about this is that really this is just measuring the excess or additional cost that you're incurring in excess of what you could have achieved had you known the disturbance at the outset. And this is actually, so connecting to Caltech, was originally proposed by Goel and Hasibi, which in a very wonderful paper. I suggest that if you're interested in these kinds of problems, read this paper. It was kind of the inspiration for this work. So, okay. So the problem that we want to solve, here we're going to assume we have an ambiguity set of distributions. I'll make that more explicit in a moment. Minimize over your class of causal controllers, maximize over the distribution, right? Expected, regret. Okay. In this paper that I mentioned, they consider a related problem that considers a slightly different model, right, disturbance model. They're assuming the disturbance is non-stochastic adversarial. So they're minimizing worst-case regret over a norm ball of disturbances. Okay, so think of this as an energy bound. And there's been a number of follow-up papers building on this framework here, which add constraints, look at the partially observed variant, and so on. This paper by Seiler is very interesting because they also account for plant uncertainty, okay, uncertainty in the dynamics. How much time do I have? Okay, all right. Now, I think one of the limitations of a framework like this is that it ignores statistical information. So if you have knowledge, additional structure about the disturbance process in the form of a distribution, you may want to exploit that. Okay. All right. So the results in this talk are very elementary. Okay, it's just basic linear algebra. There's nothing kind of fancy. So this is essentially a self-contained talk. So the cost realized by any controller, potentially non-causal, right, can be decomposed as the cost incurred by some controller K star, which we'll interpret in a moment, plus this quadratic expression here in W. Okay, and this was actually, as far as I'm aware, this decomposition was first proposed in this monograph by SCB in 1999 on indefinite quadratic estimation and control. So D is a positive definite matrix, right? R is positive definite. This is positive semi-definite. So this matrix here is positive semi-definite. So this is non-negative for all W and K, right? Hence, right, the left-hand side is greater than or equal to the right-hand side for all K and W, and that implies that K star is in fact the optimal non-causal controller. And you can show this using, this decomposition just follows from a completion of squares with respect to U. So what that means then is that this is in fact the regret, right? Which is just like a weighted difference of your controller K and the optimal non-causal controller. And we'll write that more compactly as this quadratic expression. So CK here is this matrix which depends on your controller K and the non-causal controller K star. Okay, so to the ambiguity set. So in the paper, we actually consider a different class of ambiguity sets based on the type 2 Wasserstein distance. Here we're going to consider a simpler class that I think is a little more informative, or easier to more transparent, I think is the right way to think of it. So the expected regret, right, just the expectation of this quadratic, right? You could take the trace of the scalar, right, and then just permute, and you end up with the trace of CK times the second moment of W. So your expected cost only depends on the distribution through its second moment. And so we'll consider an ambiguity set that's essentially a norm ball centered at some given nominal second moment matrix, right, intersected with a positive semi-definite cone. And here R measures the radius of the ambiguity set or the degree of confidence you have in like the correctness of this nominal second moment. And the norm here that we'll consider is the nuclear norm ball, and it'll become apparent in a moment why we're using nuclear norm. You can consider different norms, but this is nice because it'll allow us to explicitly connect with this other framework that I mentioned to you. So this is now a reduction of the problem that we want to solve, right? I'll skip this, it's very elementary, right? You can essentially reformulate it as the expected regret. So this first term here is the expected regret under the nominal second moment, plus some form of regularization. So this is the induced 2 norm or the spectral norm of the matrix CK weighted by R. So this is actually equivalent to the problem in which you're minimizing the expected cost under the nominal distribution plus the adversarial regret, right, which I had mentioned to you earlier, right, weighted by R. And so it's like a mixed objective here, mixed H2, robust regret optimal control objective. But what's nice is R allows you to kind of smoothly interpolate between the nominal H2 criterion and this robust regret criterion. You can reformulate this as a semi-definite program, but for large instances, it's actually much more efficient. We found that projected subgradient methods, so this term here is not differentiable, it's right non-smooth, are very effective. Now, I will say the underlying norm, right, matters. It determines the form of regularization, and so that kind of ultimately comes back to, what kind of robustness do you want to imbue your controller with, right? What kind of shifts, distribution shifts, do you expect to see? Do I have 1 minute to do this example? Okay, so I'll do the example. All right. So this is an example, like an application of this technique to a data-driven control problem. So again, very simple, just for transparency. It's a controlled random walk. These are scalar variables. We have we're just penalizing a standard quadratic objective in our state and inputs. And here the distribution, the true distribution, is just, we're going to assume is Gaussian with a constant mean, so a constant signal plus Gaussian white noise, okay? All right, so that's the true distribution. So the data-driven part of this problem is we're going to assume that you don't know the moment, right, the second moment, or you don't know this distribution. But you have data, so here we're assuming we have n IID samples from this distribution. I think we use 15 samples. And then you just estimate the nominal moment as just the empirical second moment based on this data, right? And so let's compare the two different control designs, this distributionally robust approach and this, what we're calling the minimax regret, or MRO, optimal control approach. So the green line here is the optimal causal controller, the cost achieved by the controller that knows the distribution, right, at the outset. And the red curve here is the cost achieved by the distributionally robust optimal controller as a function of the radius of the ambiguity set R, right? So this, for R equal to 0, you're essentially solving a sample average approximation, an H2 problem using the empirical second moment. As you increase the radius, you improve generalization. This is the expected cost averaged over some number of trials of the resulting controller under the true distribution, right? But what's interesting is this other extreme, this is actually the H infinity optimal controller, right? Which is achieving, which is kind of worse than what you're seeing. It does worse than the sample average and worse than the optimal DRO. Now, the MRO controller kind of improves upon both. So it generalizes slightly better for certain radii, and asymptotically, right, converges to the robust regret optimal controller for very large radii. You can think of the worst case distribution, right, under this control design, or the worst case second moment, as becoming degenerate, right? You're converging to a distribution which is putting all of the mass on a probability mass on a single disturbance, which corresponds to the worst case disturbance in this framework. Okay, so to conclude, these controllers, they're essentially regularized H2 optimal controllers. The choice of norm matters. They interpolate between the nominal H2 optimal controller and the robust regret optimal controller. And in some, it seems, you know, we have a variety of examples. In some cases, they can improve generalization in data-driven settings. There are many extensions. So as I mentioned, Seiler looks at a framework that accounts for model uncertainty. There's been some very nice work done here at Caltech, extending this framework to partially observed systems, to the infinite horizon. I think there's also, it would be interesting to apply these techniques to filtering problems. Okay. And then finally, I guess, you know, one of the motivations was kind of defining the baseline in terms of the causal controller. It'd be interesting to see if that problem can be solved efficiently, right? So weakening the oracle, okay? And that's it. Thank you.